Okay guys, so today's lesson is going to be 9-7, and we're going to be talking about wholes and asymptotes of rational functions, okay? So just bear with me, it's going to be a lot of talking, but you guys should be able to know what's going on at the end, okay? So, wholes and asymptotes of rational functions. So I give you this little snippet right here, that we're going to go ahead and call points of discontinuity. Okay, so go ahead and take some time to kind of read what it has over here. I'm going to go ahead and summarize it for you guys. Okay, so this first paragraph right here is basically telling you that A, okay, is a real number. Okay, it is a real number right here. Now, here it is telling you that A is going to be 0. Okay, and we're talking about A in the denominator. Remember what we said? You cannot have a denominator of 0, right? So if you have a value of A that is a 0, you are going to have a point of discontinuity at x equals to A because the denominator cannot equal to 0. Now, if you have a denominator again that does not equal to 0, right? So there is no value of x that makes the denominator 0. You are going to have a continuous graph because there is going to be no jumps, breaks, or holes. So that means that you can draw the graph on your pencil and never ever stop, right? So basically what happens when you have a denominator of 0, right? So when you have a denominator of 0, you will have discontinuity. Okay, will cause discontinuity in the form of jumps, breaks, or holes. Okay. Okay, now when you have no denominator of 0, okay, graph will be continuous. Okay, so these are two important main points. So when you have a denominator equals to 0, you're going to have discontinuity. When you have no denominator equaling to 0, the graph will be continuous. And so now over here, we're going to have a removable discontinuity because if you notice the denominator here is x plus 2. So if I put a negative 2 for that x, that becomes 0, right? So you have a removable discontinuity at x equals to negative 2. If you notice right here, what did they create? A hole. Okay, so that's a hole in the graph, which is called a removable discontinuity because you can make the function continuous by redefining it at x equals to negative 2. Now, on the other side over here with this x minus 2, this is a non-removable discontinuity. Now, the way that I think of non-removable discontinuities is I think of them as being asymptotes, right? Because you cannot get rid of an asymptote at all. The asymptote is just going to be an invisible line that is always going to be there. So, therefore, this would be a non-removable discontinuity at x equals to 2. Because there's no way that you can redefine the function like it says here to make the function continuous. It's just always going to be discontinuous because of the fact that it has an asymptote. Okay, and these are literally the key the vocabulary definitions that I am going to be using throughout today's lesson. So with that, let's go ahead and look at example number 1. Okay, so what we're going to do is we are going to find points of discontinuity. So we want to know what are the domain and the points of discontinuity for each rational function. So I'm going to give you multiple questions, okay? Are the points of discontinuity removable or non-removable? What are the x and y intercepts? So this is it's going to tie into the lesson about the key attributes of rational functions, okay? Because we did find the x and the y intercepts in that lesson. So that's what I'm going to be referencing to today in this lesson. So whenever you're trying to find discontinuity or continuity, the first thing that you're going to do, because your graphs or your functions are going to be in this form where you have trinomials and binomials, is that you are going to factor the numerator and the denominator. Okay, you want to factor the numerator and the denominator because both of these are going to help you figure out either the domain, the range, the x or the y intercepts. So you need to make sure that you factor the numerator and the denominator. Okay. So if I look at this, the numerator x plus 3, can't really do anything there. That's already as simplified as it can get. But this x squared minus 4x plus 3, I can go ahead and I can factor it out. Now, like I said, I'm going to do this in my head, but if you guys want to, you guys can use the reverse tabular or tic-tac-toe to factor that out. But I'm just going to go ahead and move on. So I know that I'm going to get two factors from this with an x and an x, and then I need something to multiply to 3. Well, what's the only two numbers that multiply to 3? That's 3 and 1, okay? Now, I do need them to equal to a negative 4, so I'm going to make both of these negative, because a negative 3 times a negative 1 is a positive 3, but a negative 3 minus 1 is a negative 4, so that fits perfectly. And I'm going to go ahead and I'm going to put the x plus 3 in my numerator. Now, remember, guys, if you want to know when something is undefined, right, you'll get the denominator and you equal it to 0, right? So if I want to know what is undefined, I have to get the denominator, okay, and I equal it to 0. Okay, doing that will tell me what values are gonna make this function undefined. So I get the x minus 3, equal it to 0, and then the x minus 1 and equal it to 0. At the 3, x cannot equal to 3, okay? At the 1, x cannot equal to 1, because if you do that, you're going to get a 0 as a denominator, which therefore would be undefined. So this will be undefined, okay? At x equals to 3 and x equals to 1, okay, cannot equal to those values. And so the domain for this, okay, because we have to find the domain, is going to be all real numbers except x equals 3 and x equals to 1. Why? Because there is where the function is going to be undefined. So it's going to be all real numbers except at those two values. Okay, now here I'm going to have a non-removable discontinuity, okay, non-removable discontinuity at x equals to 3 and x equals to 1, okay? Now, you know that this is a non-removable discontinuity because you have a fraction, right? And we said that a fraction is going to be some sort of rational function that either looks like this, right? Now, there's other functions as well that have asymptotes like this and then therefore look like that. Or you can have something that goes like this and like this with an asymptote going downwards like this. Right? So this is where you could have two non-removable discontinuities because you have two asymptotes going through here. So this is what's happening right here. It's a non-removable discontinuity because I have two factors in my denominator, meaning that I have two asymptotes. Okay? And it's also a fraction. Now we want to go ahead and find the x-intercept. Okay? Now remember, the x-intercept is when you make y equal to 0. Now, there's an even cool thing here, that when you're dealing with rational functions, if you want to find the y-intercept, all you have to do is just make the numerator equal to 0. So if you want to find the y-intercept for rational functions, make numerator equal to 0. Okay, so that's for the x-intercept. Okay, so then what's my what's my numerator? Well, my numerator is x plus 3. So what I have to do, make that equal to 0. So I subtract that. And that means that my y-intercept is going to be at -3, 0. Okay? Now let's find the y-intercept. When do you find the y-intercept? When x is equal to 0. So all you have to do is get the equation and replace all x's with 0. Replace all x's with 0. Okay, so that means that I'm going to go ahead and get my function. Let me use a different color. And I'm going to get y equals to 0 plus 3 over 0 minus 3, and then 0 minus 1. Okay, so then that 0 plus 3 is 3, and then 0 minus 3 is -3. 0 minus 1 is -1. Well, what's -3 times -1? 3. So 3 divided by 3 is 1. So my y-intercept is going to be 0, 1. And that is how you solve that problem. It took me a little bit longer just because I was trying to explain everything in detail, but the rest of them we should be going through a little bit smoothly. So let's go ahead and go to example number 2. Okay, so we're going to go ahead and begin example number 2 by factoring. Okay, so now if I look at this, okay, is there anything that I can factor? Well, the numerator is already factored. The denominator, you cannot factor it because you cannot do difference of squares since this right here is a plus sign. So that's already as simplified or as factored as it can get. Now, I need to try to see, is there something that can make my denominator equal to 0? Well, I do see that I have an x squared plus 1. So that means that whatever x squared is, I'm always going to be adding 1 to it, right? So I can say, let's say 1 squared. Well, what's 1 squared? 1 plus 1 is 2. You can get 2 squared plus 1, that'll be 5. You can also do a negative. A -3 squared, that's going to be a 9 plus 1 is 10. So there really is no number that you can put for x to make it equal to 0, right? So here in this situation, in this specific situation, my denominator cannot equal to 0. Okay, so that means if my denominator cannot equal to 0, then this function is continuous. Okay, meaning that you will have no points of discontinuity here. So that means that if I try to graph this, is this going to be like my typical rational function here? No, it's not. Okay, and I'll try to graph these for you guys later so you guys can see what these look like visually. But this right here is going to be a continuous function, so there's no point for me to look where something is undefined or for me to try to figure out, is this going to be removable or non-removable, because there's going to be no discontinuity. This is 100% continuous, okay? Because the denominator cannot equal to 0 in this situation. My denominator cannot equal to 0. Okay, no matter what number you choose, you can plug in whatever number you want. If you guys don't believe me, plug it in. You cannot make x squared plus 1 equal to 0 at all. So, therefore, the only things that we can actually find here are going to be the x-intercept and the y-intercept. So for the x-intercept, remember, you just get the numerator and you equal it to 0. So I'm going to add the 5, So my x-intercept here is going to be 5, 0. Okay, and now for the y-intercept, we have to get the x to equal to 0. So that means just get the whole function and replace it with 0. So y equals 0 minus 5 divided by 0 squared plus 1. Well, what's 0 minus 5? -5. 0 squared is literally just 0. Plus 1 is 1. So -5 divided by 1 is going to be -5. So my y-intercept here is going to be 0, -5. Okay, and that is all for this problem. Okay, moving on to the third one. Okay, so now let's work on the third example. First thing is going to be to factor. Okay, numerator, I need to factor denominator, not so much because x minus 4 is already factored. So let's go ahead and factor the numerator. I'm going to have two binomials, x and x. What numbers multiply times 4, but then probably going to give me 3, so I'll do 4 and 1. Now I do need it to multiply it to a negative 4, so one of these numbers has to be negative, either 4 or 1. Seeing that it needs to add to a negative 3, I'm going to make the negative 4, the 4 negative, and then I'll keep the 1 positive divided by x minus 4. Now, I factored this, okay? Is there something that I can eliminate? Yes, there is. This x minus 4. So if I eliminate the x minus 4, I'm literally just going to be left with x plus 1. And if I'm left with this x plus 1, my rational function kind of just like disappears, right? Because now I don't have a denominator. So what this means, okay, is that I am now going to have a removable discontinuity. Okay, because if I graph x plus 1, that's not going to be discontinuity. That's not going to be a rational function anymore. It's actually going to be a linear function because it's just x plus 1, right? Y equals mx plus b. So therefore here, I'm going to have a removable discontinuity. Okay, so I have a removable discontinuity because my rational function disappeared when I ended up simplifying this expression. Now, where's this removable discontinuity? Well, I still have a denominator, right? The denominator is right here. So all I have to do is just make that equal to 0. So my removable discontinuity is going to be at x minus 4 equals to 0. So I add the 4. So x equals to 4 is my removable discontinuity. Okay? So where is this going to be undefined? Well, this is going to be undefined at x equals to negative 4. I mean, undefined, not negative 4. I mean, x equals to positive 4. Okay. And so we go ahead and continue. So let's go ahead and move on. Now we want to find the x-intercept, which is when y equals to 0. Now literally you just have x plus 1, right? So you have y equals x plus 1. So you set the y equals to 0, subtract the 1, and x is going to equal to negative 1. So your x-intercept is when x is negative 1 and y is 0. Okay? So now let's find the y-intercept, which you get when x equals to 0. So we're going to use the original function, y equals to 0 squared minus 3 times 0 minus 4 over 0 minus 4. Well, 0 squared is 0. Negative 3 times 0 is 0, minus 4. 0 minus 4 is negative 4, so that's just going to be negative 4 divided by negative 4, which is going to be a positive 1. So my y-intercept is going to be 0, comma 1. Okay? Okay, now I'm almost done, but I just wanted to go ahead and show you what the removable and the non-removable discontinuities look like. So example number 1, this one in red, it was the first example that we started with. So this was example A. Okay, and now we said that this here had a non-removable discontinuity. Okay, now, the reason why it had a non-removable discontinuity is because it has discontinuity is because it has asymptotes, right? So when you have asymptotes, you literally cannot get rid of them. You cannot get rid of them. So therefore, they are non-removable because it is going to be discontinuous. But you cannot take them away because it will just always have those asymptotes. And so that's kind of what that's going to look like. Now, for example B right here, which is the second example that we did, this one right here was continuous. Okay. This one had no discontinuity. It has no asymptotes. It has no holes. It has nothing because you cannot make the denominator go to 0. So I could literally get my pencil and trace this graph and never pick my pencil up because it will always, always, always be continuous. Okay. And now for example C right here, this one has a removable discontinuity. Okay. Now what distinguishes a removable discontinuity versus a non-removable one is that this one doesn't have asymptotes, right? So this is no asymptotes. Okay. So when I graph this at x minus 4, that means that x cannot equal to 4 because that will be a discontinuity, is that I would go to 4, and here I would draw an open circle. Okay, so just keep that in mind. So that's the difference between a non-removable, a continuous graph, and a removable discontinuity. That's what they'd look like. Now, are all of the graphs going to look like this? No, but the general idea is going to remain the same. That you're going to have an asymptote, therefore non-removable. You may have no asymptotes, therefore removable, or it might just be continuous and never ever ending. Example B. Okay, have a good one.